Hi, welcome to my channel, Math Made Easy with Laurel. I'm Laurel, and in this video we're going to continue our work on finding volumes using the shell method. In the previous video, we talked about how we found the volume using shell method when we had vertical rectangles rotating about the y-axis. In this, we're going to do the same thing, except we're going to use horizontal rectangles. And we're going to rotate those rectangles about the x-axis. Because they're parallel to the axis of rotation, we're going to use the shell method. And we learned in the last video that the volume of a shell is equal to 2 pi r times the height times the thickness. So if you haven't watched that video, I strongly recommend you watch that first where I explained it in more detail. Now we're working with horizontal rectangles, which means we're working with everything in terms of y. We're working with our functions in terms of y, and we're working with the limits for our integral in terms of the y values, not the x. So if we wanted to find the volume generated by this area rotated around the x-axis, we would sum all of these individual slivers or rectangles from C to D using integration. And in our formula, 2 pi is a constant, so we'll pull that outside of the integral sign. So we're going from C to D. And we're working with the radius that's formed. So the radius that's formed from this rectangle as it's rotating about the x-axis will be this value, which is y. So the distance from that rectangle to the x-axis is y. Then we're going to represent the height in terms of our function. So the height of this rectangle, or the length of this rectangle, will be f of y, which is the right curve, minus g of y, which is the left curve. And then we multiply by the thickness of that shell, and that thickness of that shell will be dy. So very similar to what we did in the previous video, but now we're working with horizontal rectangles, which means we're doing everything in terms of y. Let's take a look at an example. Our example says, find the volume of the solid generated by revolving the region bounded by y equals x cubed, y equals 1, y equals 8, and x equals 4 around the x-axis. So we're rotating around the x-axis. And let's draw all of those functions. Y equals x cubed, y equals 1, y equals 8, and x equals 4. We have to have an idea of where that vertical line is in terms of these points here. Are they inside or outside? So we need to really determine what those x values are. So when y equals 8, x would be the cubed root of 8 would be 2. So x equals 4 is out here. You want to know if it's outside of that point or within that. So there's lots of regions here, but we're looking for the region that's bounded by all 4 of those things. So this, 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 and this. So this is the only region that's bounded by all 4 of those curves or functions or lines. And we're going to take this region and rotate it about the x-axis. So what we're going to do is we're going to use horizontal rectangles. If we were to use vertical rectangles, we would have an issue because this region is defined differently than this region. So we'd have to do 2 separate volumes and then add them together, which you can do. But I want to do this with horizontal rectangles. And because my rectangle is parallel to the axis of revolution, that means I'm using the shell method. If your rectangles are perpendicular to the axis of revolution, you can't use shell, you'd have to use washer or disc. So we're going to use shell method. Because we're using horizontal rectangles, we have to have everything in terms of y. So we can't use y equals x cubed. Instead, we have to write x equals y to the 1/3. It has to be a function of y. So now we can set up our integral. It's going to be the y values 1 to 8, y times f of y. So f of y is going to be our right curve. So this is our f of y. This is our g of y. It's our left curve. So that would be y to the 1/3. Let's simplify. Add the exponents. Now we can integrate. The integral of 4y dy is 2y squared minus the integral of y to the 4/3 will be 3/7 y to the 7/3. When I evaluate this, I'm going to pull the 2 pi right out because it's going to be a factor of both values when I put an 8 in as well as when I put a 1 in. And then I'm going to put an 8 in, so 8 squared is 64 times 2 is 128 minus 3/7 times cubed root of 8 is 2, so 2 to the 7th. Two times 1 squared would be 2 minus 3/7 times 1 to any power is 1, so 3/7. When I simplify this and calculate it, I'm going to write it as 449.7 cubic units, rather than getting into a fraction with 7 as the denominator. Sometimes you may be asked to find the volume when your area is rotated around a line other than one of the axes. So I want to do an example of that to show you how shells is very convenient for doing that type of calculation. So let's take a look at that. So if we had the question, find the volume of the solid form by revolving the region bounded by y equals x squared plus 2 and y equals x plus 8 around the line x equals 4, we're not revolving our area around an axis. Let's set up the graph first, and then we'll talk about how we set up the integral. So y equals x squared plus 2 is just the parabola for x squared, but it's just shifted up 2 units. Then y equals x plus 8 is a straight line, slope of 1, y-intercept of 8. So we're taking this region here. Now before I draw the line x equals 4, I want to know what this point is, because I want to know whether 4 is outside of that or not. So let's find our points of intersection before I draw the line we're rotating around. So points of intersection will be when x squared plus 2 is equal to x plus 8. Move everything over so it's equal to 0. We can factor, so our factors will be x minus 3 and x plus 2. So x equals 3 and x equals -2 are my 2 points of intersection. Now I know my line x equals 4 is outside that. I just moved the function definitions out of the way. Now I can draw my line x equals 4. So we're taking this region and revolving it about this line. The easiest way to do this is using the shell method. We're going to take a representative rectangle, which will be vertical, and rotate it around that line so it creates a shell. Because we're not rotating this around one of the axes, we have to be careful when we come up with the formula. We can't use the formulas that we've learned. We still use the formula for finding volume of a shell, but what we have to really be careful about is how we define the radius, because we're not using the axes. So let's take a look. We'll pull 2 pi out. We know our limits, it's -2 and 3. So to define the radius, I have to know how far away from the line of rotation is my representative rectangle. Well, I know this distance is x right here, and I know the distance from here to here is 4. So I need to be able to define this distance from this rectangle to the line of rotation. It will be 4 minus x. That's the toughest thing for students to find. You have to look at where that rectangle is, how far is it from your line of rotation, and determine how to express that in terms of your x or your y, depending on whether you're using vertical or horizontal rectangles. So the radius of the shell that's formed will be 4 minus x. Now I express the height of this rectangle. So it will be the top curve, which is x plus 8, minus the bottom curve, which is x squared plus 2. Times the thickness, which is dx. That's how we would find the volume of the solid form by taking this area and rotating it around this line. Let's simplify first. When I simplify in here, I'm going to have x, and I'm going to have 8 minus 2, so that will be plus 6, minus x squared dx. Now I'm going to multiply all of this so that I have one polynomial. So when I expanded this by multiplying 4 to each of the terms in this polynomial and negative x, and then I combine like terms and then express them in, starting with my highest degree term, I get this. Now I can integrate. So I'm going to have 1/4 x to the 4th minus 5/3 x cubed minus x squared plus 24x. I'm now going to put a 3 in for x, then a negative 2, and subtract the two quantities. And when I do that, I get a value of 875 pi over 6 cubic units. I think this is probably the most challenging volume you're going to find, is when you have your area rotated around something other than the y or the x-axis. That concludes the video on shell method. We've now talked about 3 methods of finding volume, and I find that students get mixed up as to what method to use, and they use the wrong method with the rectangles that they choose. So I want to address that issue and provide a summary of how to know what method to use and what rectangles to use in the next video. So take a look at that, and that should hopefully clear up some of the confusion. Take care, and see you on the next video.